In the previous session, I was talking about the idea of matrix representations of operators. Now these angular momentum operators, they had a certain algebra, for example commutation, relations and so forth, and the corresponding matrices, the equivalent matrices, behaved the same way. For example, if you took a commutation relation between two operators, square brackets a hat comma b hat, then the result that you'd get would be the matrix equivalent if you did that commutation relation between the corresponding matrices. So the operators and the matrices behave in corresponding ways. So in a sense, this technical term of representation is used because in a sense the matrices are talking the same language, so to speak, speaking metaphorically, as the operators. They're behaving the same way. And we mentioned by doing this kind of thing, we defined earlier the equivalence between an operator and it's like a Hermitian operator and a Hermitian matrix. We found the matrix element by having an eigenfunction operate an eigenfunction, well, the overlap integral effectively. Okay? And in the case when we were using for the eigenfunctions, we were using the spherical harmonics. This expression is 0 if the L and L dashed here are different. So I've put this as L here. They're both L. In that case, it's non-zero. But this leaves you more possibilities than just using simple eigen functions like phi n, where phi n ranges from little n ranging from 1 to big N kind of thing. In this case, since this is non-zero for m and m dashed, your m can range over, it can have 2l plus 1 different values, and similarly for m dashed. So the total number of elements here is 2l plus n all squared. Okay? And L, L's the angular momentum. As it increases in size, larger and larger L's, you can have more and more matrix representations of this operator. The operator in this case is L squared, but you can have equivalent matrices that behave in the same way, the same commutation relations and that kind of thing as the operator here. But effectively, infinitely many of them. You can have infinitely many representations. Okay. Now, so I'll talk a little bit more about that, but I'll go a little bit off on a tangent because it's probably a good moment. What you're seeing here is just scratching the surface, just touching a little on representation theory, which is just a huge topic in its own right in pure mathematics, and very important for group theory. So in that context, I'll show you a few books of courses that I will be teaching on representation theory in the future at M1 and M2, first year masters and second year masters levels. Now, it's particularly in the context of having matrix representations of group elements. Now, this might be a particular case. This thing here is an operator. It's a angular momentum type operator, and so that you may have a set of these that may form a group in the mathematical sense, mathematical group. I hope those of you who are following this course in quantum mechanics also followed my previous course, also at senior, more or less senior level, on group theory. So representations are very important for groups. So I'll show you the first book here. So this is an M1 level course, so I'll be teaching from this textbook in about a year, I guess, the way things are going. So it's called Representations and Characters of Groups. It's by James and Liebeck. It's a rather famous text. It's 400 pages, so it'll take a while. So here's the text. Okay. And what's the importance of representations? They're a particularly powerful way to how can I put this? If you know how to manipulate the representations of groups, that can tell you a lot about the groups themselves. There's a lot of information contained in representations about which is information that about the groups. And also, if you're using matrix representations, then you can then use the techniques of linear algebra on those matrices, like taking the sum of the diagonals, which is it's sort of the so-called trace. In some ways it's easier to deal with the representation of a group member than the group member itself. So ease of use is one major reason. Also, if you're a bit fuzzy on what the group elements are, what the nature of the group is, say you're investigating stuff, then often you can find out things more easily about the nature of the group than using representations of a group than the group directly. So there's another reason. There's lots of reasons. Group representations are very important in Lie theory, as in Lie groups and Lie algebras, and I'll be giving a lot of courses on those in master's level M1 and M2. Like here's the text on Lie algebras for M1 level that I'll be giving in about a year or so. It's called just simply the Lie algebras SU of n. SU means special unitary. It's a particular type of matrix group. Right? Here's the text. Okay. And SU3, where n is 3, that's the number of dimensions, n. SU3 is very important in the classification of the elementary particles. So what Mendeleev did to the elements in the 19th century, Gell-Mann and others did to the classification of elementary particles in the mid-20th century, more or less, using these ideas. And what are Lie groups and Lie algebras? Well, a Lie group is effectively a continuous group with an infinite number of members, and the parameters in those groups can change smoothly, continuously. So effectively, an infinite number, often uncountably infinite number of members, and so they're in a sense infinite groups, and play a huge role in physics. So an important part of any mathematical physicist's education, definitely. And talking a little bit about characters. Without getting too technical, I don't really want to explain what a character is in the context of groups and representations. But it's a concept that comes out of representation of groups, which makes manipulating these representations, or these are just called reps, R-E-P, a representation, a matrix representation of usually a group member. In this case, in this context, angular momentum, a matrix representation of a angular momentum operator, or L squared, LZ, whatever. So here's the text that I'll be using M2, second year master's level, on matrix representations, particularly concentrating on the concept of character theory. And character theory is something that comes out of matrix representations. I won't give you the definition. It's like, it's 2 levels above what we're doing now. But just for interest. So, another classic text is by Isaacs, Character Theory of Finite Groups.